Good morning, everyone. My name is Stefano Patruno. I'm a geologist with several years of direct work experience in the oil and gas industry. Lately, I've been working full-time as a lecturer at the University of Nicosia in the Department of Engineering in Cyprus. And today I would like to talk to you about the recent excitement regarding the new natural gas resources that have been found and that are still being explored in the Eastern Mediterranean. In particular, the petroleum geology aspect of it. This is a very low-level introduction. I will try to be very, very simple so that everybody can understand, particularly the non-specialists out there. So I would like to start off with a map of the Eastern Mediterranean that you can see over here. In this map, there are several colored objects over here. Each of these colored objects represent a current discovered natural gas accumulation called field. Okay, so there are several of them in the Egyptian exclusive economic zone, some in the Cypriot exclusive economic zone, some in the Israeli exclusive economic zone. And active exploration is still ongoing. But today I would like to talk to you in particular about the most exciting of all of this discovery, which is called Zohr. This is, which is over here. As you can see, it's located in the Egyptian exclusive economic zone, not too far away from the southern border with Cyprus. Why do I say that is particularly exciting? Well, it's a recent discovery, 2015, done by ENI. And first thing, it's very, very, very large. It is 30 TCF of natural gas in place resource, trillion cubic feet, 30 trillion cubic feet. That makes it the 20th largest natural gas discovery in the whole world, roundabout, approximately. Which is a remarkable achievement, and certainly the largest discovery ever in the Mediterranean and in the whole of Egypt, including onshore Egypt as well. So that's the first reason of the excitement. The second reason of the excitement is that this discovery is a completely new geological idea. It's called geological play, new geological play, that people never thought about before that could exist. Okay, so since 2015, since Zohr has been announced, there's been a resurgence of interest in exploration for deep marine natural gas in around Egypt, but also in Cyprus and surrounding countries, trying to apply the same concept that has proved so successful in Zohr, trying to recognize other mini Zohrs or same size as Zohrs popping up around. And there's already been some success, such as Calypso, that was discovered last year in 2019 in Block 6 of offshore Cyprus. Now, the consequences for the economy of the nations facing the Eastern Mediterranean is for sure going to be a positive one. Think about Egypt, which has got a very large population, very, very large population. But last year, since discovered Zohr, some additional new recently discovered natural gas fields, it has announced that it has become a net exporter of LNG, liquefied natural gas, which has been a truly remarkable achievement. Okay, but before really going into the concepts of petroleum geology, I would like to make one additional remark. So I talk about the benefit to the economy very quickly of nations and of the greater region at large, which are probably very, very substantial. But natural gas, it's also likely to be a key for the future low carbon economy, because natural gas is uncontroversially the cleanest of all the fossil fuels. For example, when we burn natural gas, we only produce methane, we only produce energy as heat, water, H2O, and CO2. Okay, so that means no additional pollutant compare it with some other fossil fuels, for example, with coal, which is one of the worst offenders when it comes to green matters. Well, coal, apart from CO2, also produces a lot of additional pollutants, including sulfur dioxide, which is one of the major causes of acid rains, for example. We wouldn't have any of these problems by just using natural gas. Additionally, and importantly, natural gas, methane, is one of the most CO2 efficient fuels, because look at this graph. So basically, this graph shows the amount of CO2 emitted by several fossil fuels per unit of energy produced. So as you can see, natural gas only produces 0.2 kilograms of CO2 per kilowatt for each hour. Compare it to lignite or peat or coal, which are all much larger figures. In particular, we can say that natural gas produces 30% less CO2 per unit of energy than oil, and even more than 40% less CO2 per unit of energy than coal. So indeed, CO2, natural gas is this part of the transition towards a carbon light economy. And this is a conclusion of many independent analyses, including this one by International Energy Agency in 2019, saying that natural gas is one of the mainstay of global energy, where it replaces more polluting fuels, it improves air quality and limits emission of carbon dioxide. And this is, again, a kind of an uncontroversial statement. So let's start thinking about what the petroleum system is. How does it look like? Well, if you have no experience whatsoever in this field, just think about the simple experience of pouring a liquid from a bottle into a glass. Okay, that can be champagne, for example, or it can be any other liquid for that matter. So it's a very simple thing, but it comprises several actions and several objects interacting with each other. So let's try to describe these various objects. First of all, we have a bottle which initially contained all of the champagne. Okay, so let's call this bottle a mature source of champagne. Yeah, a source of champagne. Then this bottle has been lifted, inclined, and some of this champagne has been pouring down, right? Pouring down like this towards the glass itself. Let's call this action of pouring down the champagne the primary migration of champagne. Okay. On the surface of the planet where we all live, every time a liquid, a fluid, or even a solid for what matters, is free to move, it will move downward. Why? Why? Because we are all subject to the acceleration of gravity acceleration, which is all pushing us down towards the center of Earth. Okay, so everything moves downward. That's why when the champagne is free to move, it will fall down. Okay, another uncontroversial statement. Lots of uncontroversial statements today. Then where does it go, this champagne? It will go over here. It will go on this glass. Okay, glass which is made of crystal, if you are posh, or is made of plastic, maybe. Okay. What's the shape of the glass? It's a bucket shape. Okay, it's essentially, if you want to be more precise, concave shape. Okay, concave upward shape. Why do we have this shape? Because people have understood pretty quickly that that's the most effective shape to hold in place a certain amount of fluid. Okay, a certain volume of fluid. Concave upward shapes. If you had used the concave downward shape, even with the best material, no liquid would have been remaining in there, but everything would have gone down even further, dirtying your floor. And also glass consists of two areas. Let's call two areas. The glass wall, which as I said is made of crystals or plastic or any other impermeable material. What do we mean by impermeable material? A material that stops fluids from further movement. Okay, so that's very important, because if you don't use impermeable material, again, the champagne would not stay in place, but keep on trickling down. For example, if the glass is broken, it would trickle down and it would dirty your floor. And second thing, in a second space in a glass, it's the empty space inside the glass itself. Okay, this empty space inside the glass itself is what is actually filled with the champagne. Yes. So let's call the glass surface, or the plastic or the crystal, a seal material for the champagne, and let's call the empty space inside the glass itself the reservoir for champagne. And let's call the shape, this concave upward shape of the glass, let's call it the trap for the champagne. Okay, so we've introduced 5 terms until now. We introduced source for the bottle of champagne. We introduced the term migration for the action of the champagne that is pouring downward. We've called the glass the trap for champagne. The surface of the glass, we've called it the seal material that stops the champagne from trickling down. And the empty space inside the champagne, we called it the reservoir for champagne. Another thing we can say is that this trap is underfilled at the moment. That means that there is still empty space, there is still a reservoir space that can be filled with further fluid. When finally the champagne reaches this level, then we can call it fill to spill. Okay, so yeah, here you go. Mature source of champagne, primary migration champagne. Each of the glass is a trap of champagne, crystal is the seal, reservoir is the empty space. Trap still underfilled. So this is all remarkably similar to what happens in the subsurface, so under the surface of the Earth. Why are we talking about what happens under the surface of the Earth? Because all oil and gas is created under the surface of the Earth in the subsurface, and it's also accumulated there. You know, we have to drill wells in order to find it. So under the surface of the Earth, we will have source rocks, we will have migration, we will have reservoir, traps, all the same things, only upside down from our champagne experience. Why that? Because fluids under the surface of the Earth will tend to move upward, particularly hydrocarbon fluids, gas and oil, because they're particularly low density compared to water, and compare, of course, to the surrounding rocks. That's the type of materials that you will find in the subsurface. So every time hydrocarbons are free to move in the subsurface, will tend to move upward and not downward, like our champagne on your table. You know, will move upward under the effect of its buoyancy, its overall buoyancy. So therefore, the only difference from our champagne experience that we will need a concave downward, something looking like a dome. Okay, something looking like an upside down bucket, like your bucket when you used to be a child that you do sandcastle with. Okay, concave downward shape to hold hydrocarbons in place. That's the first difference. The second difference I already mentioned is that the migration will take place going upward and not downward. Okay. So you go, mature source, primary migration, so on and so forth. Trap still underfilled. Okay, so metaphors aside, that's what a true petroleum system looks like, and it is, as I said before, surprisingly similar to the champagne experience. So this is a well, okay, going down. That's the surface. That's in blue, it's the seawater. Then this is the surface of the seafloor, and then all the other layers that are underneath All the other layers in orange, in blue, and so on and so forth, they're all rock layers, and particularly sedimentary rock layers. Okay, so these rocks, they're deposited in layers. They form horizontal layers, and then they are eventually deformed in certain cases. So what do you see over here? First of all, you see a shape like this. How can you describe a shape like this? Well, concave downward, right? Concave downward, which is exactly like our champagne glass, which is being top down. Okay, so that can be a perfect trap shape for a fluid that is rising upward. First thing, so that's a trap. Second thing, yeah, concave downward is a trap. Second thing you see is this rock layer over here, which has been called here source rock. So that's basically the equivalent with our champagne bottle. Why do we call that a source rock? Because it's a rock full, very rich in organic matter, meaning the remain of the bodies of long dead living organisms that were alive around the time of the dinosaurs, let's say several million years ago. And then these bodies, these little remains, the little organic remains, have been going to the bottom of the floor, of the seafloor that was present at the time, and then it was slowly buried downward, forming a rock, forming an independent rock, which is called a source rock over here. And as they were going downward, it was going to be pushed downward under the weight of the younger rocks. Rock layers, younger and younger rock layers were accumulated on top. As a consequence, this source rock is eventually subjected to enough pressure and temperature that the organic matter it undergoes maturation, is called. Same saying, the maturation, how the grape juice, the initial grape juice, matures into champagne, right? So, and this process of maturation requires, as I said before, a certain amount of temperature and pressure. And following that, oil and gas is born. So oil and gas is created in this source rock. That's the factory, the initial factory of oil and gas. From the moment it's created, where do you think the oil and gas will want to go? Upward, as I said before, because it's particularly low density, so there is a lot of buoyancy pressure. So in this sketch over here, you'll see this arrow, this red arrow that signifies the primary migration, so-called, of hydrocarbon out of the source rock going upwards. And then in this case, we were lucky because the hydrocarbon has been stopped. Otherwise it could easily rise up to the surface of the seafloor and being lost forever, forming a so-called natural seep, and that can be lost forever. But in this case, it's actually stopped by the presence of a trap over here. So downward, concave downward shape, which involves both the presence of a reservoir rock here in blue, and on top of the reservoir rock, there is the seal rock. So you remember the reservoir for champagne was the empty space in the glass, right? And in fact, the reservoir rock is a rock that has got a lot of empty space, also known as pores. All this empty space can be filled with oil and gas, the migrating oil and gas. Okay, that's the definition of reservoir rock. Seal rock on top of it, similar to the plastic or the crystal of the glasses, is a rock that is impermeable, and that is also very important because it stops the oil and gas from migrating even further and eventually being lost to surface and forming a seep once more. So as you can see, we need to have these 5 elements. They all need to be there: source rock, generation and migration, reservoir rock, seal rock, see, reservoir rock, generation, migration, source rock, and finally the trap, right? Trap over here. 5 elements indispensable if you want to find an oil and gas accumulation. That's why these 5 elements, they've also been called the 5 steps to heaven. That goes without saying that if you have 4 elements only and you don't have the final one, you will not have any oil and gas accumulation eventually. So really, the fact that we still find oil and gas accumulation fields is almost like a miracle of nature. You know, it's the chances, the probability that all these five elements are all present together at the right time. Also, the right time they have to be present. To my mind, is quite low, but still, it has happened sufficiently so that we were able to find quite a lot of oil and gas until now. But surely, still a lot more oil and gas has been lost by seeping, most probably, as I said before. That's another 3D sketch, very nice 3D sketch. Showing another trap, right? That's a concave downward shape involving a reservoir rock, in this case a sandstone. We will see what the sandstone is. Capped on top by shale, which is seal rock, also known as cap rock. Cap rock as a synonym for seal rock. And here you can see the well, which is drilling down. So essentially, the oil and gas exploration, all it does is to try to, well, that sounds simple, but in effect, although the main thing that it does is finding traps in the subsurface, try to locate traps, possible traps for oil and gas, and drilling down to until you reach that trap, and make sure that this trap is full with oil and gas. In most cases, it's not full with oil and gas; it's only full with water. Yes. That's because, as I said before, you don't only need to have the trap, but you also have to have all the other elements in the right time in order to have an oil and gas accumulation. So again, it's a risky venture. In oil and gas exploration, we're always dealing with probabilities. Yeah, so most of the case, the probabilities are against you. But at least in, let's say, 10% to 30% of the cases, they are successful. So we said about reservoir rock and seal rock. Now you can see in front of you a typical example of good reservoir rock and good seal rock. So the reservoir rock, you remember, they are the rocks that have got porosity and permeability. That means they've got empty space called pores inside them that can be filled with water, but actually we don't want water, but we want oil and gas. Actually, people that drill wells to find water reservoirs, they also following the same concept, all the same concept, only that, unlike for petroleum geologists, they are looking for the reservoirs under a seal that is filled with water. So that's a sandstone, as I said before, sandstone. What does it look to you? Yes, it looks like lots of different grains, looking like sand grains that have all been cemented, sticked on top of each other naturally. That's exactly what the sandstone is. That's the same sand grains that you find at the beach and with which you play and you do sandcastle with, only after they have been buried again under the weight of lots of other more recent rocks. It undergoes processes that are called diagenesis, and eventually becomes a solid rock. All the grains are sticked with each other, and they become solid material. Another classical reservoir rock is this one. So this is limestone. It's also sedimentary rock, but it's a different type from the sandstone. It's a type that is so-called bioconstructed. That means it is essentially created by the action of living organisms, marine living organisms, that were alive many million years ago. Again, maybe at the time of the dinosaurs or after, or shortly afterwards. In most cases, living in tropical seas, they need the right kind of weather, and in clean waters, they need clean waters. Okay, so limestones and dolomite, which are closely related, they're both called carbonates. They are white rocks, very nice, sometimes well layered, sometimes less well layered, and essentially they are composed of bits and pieces of fragments of shells or skeletal parts of organisms that were alive many million years ago. And these organisms, they are marine organisms that were able to secrete calcium carbonate, as a part of their bodies, or the solid fragments. Okay. In particular, not all the limestones are good reservoir. The good reservoir, in particular, there are those that are formed in reefs. Have you ever heard about reefs? I assume so. They are the nice places where people go diving. Okay, so in offshore, in the Red Sea, I don't know, in the Antilles Islands, in the Maldives, all these nice places that present day you can find reefs. With lots of living corals, sponges, and lots of marine life in reefs. Well, essentially, reefs, through time, after all these nice living organisms, they die, they form porous rocks. And we will see some example of that later on. But I would like to jump a little bit the gun and say that the reef limestone, or the reef carbonate at least, is the main reservoir for Zohr, and also the main reservoir of all this new exciting geological place that people are looking for in the Mediterranean. Good seal rocks. This one, rather ugly looking, claystone or shale, that's essentially mud, the same mud with which you dirty your shoes after a day of rain, but once more, after that it has been buried and subject to a lot of pressure from the more recent overlying rocks, it becomes a solid material with very little permeability. That's what you need for seal rock, no permeability. So that's what we call claystone or shale. And finally, halite. What is halite? Or that's essentially the kitchen salt. Kitchen salt, the one you use for cooking, that's a rock. That's a mineral. How do we form kitchen salt? We form it by letting a whole sea or a whole salt lake evaporate. And when it evaporates, finally, all the minerals that are in solution inside the seawater, they are dropped down, they precipitate, forming layers of minerals, of rocks, okay? And we will see some example of that later on as well. But let me now introduce you to Zohr itself. Okay, that's how Zohr looks like in a sketch. This sketch has been drawn by the guys in ENI themselves that were responsible for this discovery. So it comes from the horse's mouth in a way. So let me drive you through the sketch. So that's the sea level in blue, dotted line. Then we have this black line, which represents the seafloor, present day seafloor. Then under the present day seafloor, there are all a series of horizontal rock layers, as you can see, more or less recent. And finally, we reach this purple layer over here, which is slightly older. As you go down, as you drill down, you encounter older and older sedimentary rocks, right? Remember, because the sedimentary rocks, they were formed at the bottom of a basin of many million years ago, and then they were buried under newer sedimentary rock. And then this newer sedimentary rock in its turn is buried under even newer sedimentary rock, so on and so forth, through the geological ages, through the million of years. So we're talking about this purple layer. What is this purple layer? What can you read over here? Salt. Messinian salt is called. Do you remember I just said before what's the salt about? It's one of the best seal rocks, cap rocks, right? One of the best cap rocks. And under the salt, we have this large bump here in this image. So how would you call this shape? Concave downward shape. So it's essentially like a glass upside down, like a bucket upside down. How can we call it? Indeed, we can call it a trap, a large concave downward carbonate buildup. And this blue color actually signifies what? A carbonate buildup. In simple words, that's an ancient reef, an ancient reef that was alive many million years ago, around the time of the dinosaurs and shortly afterwards. Then all these organisms died, were buried under more recent rock, and they stayed in place. And they represent essentially this reef, as I said, the actual reservoir where all the Zohr gas has been found. Laterally, these yellow layers to the two sides, what can you see? They labeled as biogenic gas. In short, essentially that's the source rock, the yellow layer. So we have a very good trap configuration with the presence of a seal rock here, the purple layers, the halite. Then we have the reef carbonate, the blue layers, and finally we have the source rock lateral to the reservoir rocks. And these arrows, these green and red arrows, they represent what? The migration of hydrocarbons out of the source rock and towards the reservoir and the trap structure. Okay, that's how Zohr looks like. It's a very nice looking, traditional, large bump, upside down bucket that has been drilled in deep water. And that's essentially how it looks like, this image to the left-hand side, in a seismic view. So this is like a view of what's under the surface in 3D in this case. So all these different colors, they basically show you this bump in 3D, this upside down bucket, the top of the carbonates. And that's basically what you can think it actually is. That is actually a mountain, a massive carbonate massive, a dolomite massive, limestone, similar to limestone, that unlike Zohr is now outcropping well above the sea level in northern Italy, in the complex of the Dolomites, that's where lots of people go skiing every year. They are white rocks, as you can see, because they are completely made of this carbonate, limestone and dolomite kind of rocks that I talked to you before. The rocks that were originally deposited by the skeleta of and fragments of shells and corals and sponges and the likes. Okay, so basically Zohr, it looks like a dolomite massif. You can figure it out like that, but buried around 2,000 meters under the sea surface, under the bottom, the mud line is called the bottom of the sea of the present day. Whereas the Dolomites, of course, they are mountains, present day mountains well above the sea level. But back in the day, when there was the formation of Zohr itself, of the reservoir of Zohr itself, this is how it must have looked like. So it must have looked like the Maldives, like atolls. That's exactly where the reefs are formed. So basically, as I said before, you need to have tropical seas, clean water, without the presence of pollution, and to get seas you also need to have a specific depth range. Okay, so a lot of people know that reefs grow where the sea level reaches, the sunlight reaches. Below this zone where the sun, which is basically lighted by the sun, reefs cannot grow, because reef is essentially a living ecosystem which depends on the primary producer, on organisms that can perform photosynthesis. Okay, so that's also very important. So the reefs, they are in relatively shallow water in this zone where the sunlight reaches, which is called photic zone. Okay, and this is how it looks like a present day living reef. One of the most extraordinary places you can go to. Really, nature living at its most. Lots of forms of life, species, everything you can think of, colors. Extraordinary, simply extraordinary. After all these things die, as they all do, their hard parts, the skeleton and their shell fragments, they accumulate at the bottom, In the case of corals, they actually stay in place. Their bodies stay in place. Their body is all made of calcium carbonate, limestone. They may be fragmented by the action of waves, destructive action of waves, and form through time rocks. It's like saying, that our skeleton, which is also composed of hard parts, of mineral parts, after we die, can also accumulate at the bottom of some place and form rocks through time. Okay. This is actually how carbonate rocks, limestones, are created, including the reservoir of Zohr. And you can see basically another nice image of a reef, and you can see basically the type of empty space, the type of pores that these rocks have. And these are all due to the presence of empty space between one little part and another of a coral body, or due to the presence of fragmented parts, including fragmented shells. That's for sure is associated to the presence of pores from one little part and the other little part. And these pores, empty space, can readily be infilled with fluids once a rock is formed and buried in the subsurface, including oil and gas. And now this is an example of an ancient reef, probably slightly late in geological age terms than the one in Zohr. But again, with all the nice mineralized body fossils that come from the type of creatures that used to live in reefs many millions of years ago. You can see here and over there. The difference with Zohr is that this one is not being buried under the sea and another 2,000 meters or more recent sediments, but is actually being uplifted by tectonic forces above the sea level, and is presently an outcrop which you can go and look at yourself in Cyprus, in an area which is called Cape Greco. Okay, so that's to say that the type of rocks that have been perforated as a very successful reservoir in Zohr they're actually widespread throughout the area, and they crop out, in this case in Cyprus, but they're also being found in lots of other wells in the offshore Eastern Mediterranean, including offshore Cyprus. Okay, we talked now about the reservoir of Zohr. Do you recall which one was the seal rock, so the impermeable rocks on top of the reservoir, which stops further migration, which stops the gas inside the reservoir and does not let it leak out and form a seep at the seafloor? Yes, it was a relatively thick layer of salt, halite. And this salt is called Messinian salt. What does it mean, Messinian salt? Messinian is just a geological age of about 7 to 5 million years ago. And it is a famous geological age. For which reason? Because during the Messinian, the whole Mediterranean disappeared. How did it disappear? Well, first of all, you have to know that the Mediterranean, it's, as you may know, a dry climate sea. As a consequence, there is a lot of evaporation going on naturally because of the action of the salt, right? Of the sun. Furthermore, the freshwater influx from the rivers, all the rivers that end up in the Mediterranean, is not enough to counterbalance the amount of sea that is lost every year to evaporation. So you can think it yourself that through the years, if the new water that comes from the river is not enough, after a while everything will be lost. Why do we still have water in the Mediterranean? We only have water in the Mediterranean because of this place. How do we call this place? The Gibraltar Strait. This is a very crucial place for the existence of the Mediterranean, because there is new water that it can flow through that strait coming in from the Atlantic Ocean. So the Mediterranean only exists because all the water that is lost to evaporation is being replaced by new water coming a little bit from the rivers, but that's not enough, and then a lot of new water coming from the open ocean, from the Atlantic Ocean. Okay. What will happen if the Gibraltar Strait disappeared? It was closed. Well, you can think it yourself. The Mediterranean would disappear. The Mediterranean would completely evaporate out. And that's exactly what happened in the Messinian age, about 5.5 million years ago. Gibraltar Strait was closed by strong plate tectonic forces. Not enough new Atlantic water can flow in, and the climate was dry, as today, or maybe even drier. And as a consequence, the Mediterranean became a giant salt lake. So you can see in this image over here, on the right here, this one, a very nice, pretty image of a present-day salt lake in Cyprus, located in Larnaca. It's a relatively famous location, very close to the international airport in Larnaca. Every summer, particularly the driest summer, you can see that this lake becomes white. Like in this case is a particular extreme example. Why does it become white? Because this lake evaporates a lot during the summer and almost disappears. And what is it created instead of the lake? All of the minerals that were initially inside the water, they were in solution with the water. They're so-called precipitate. So they come out of the water and they form a solid mineral. In this case, what's the most common mineral that you find in the seawater? When you go and swim in the seawater, you see that it's kind of salty, right? Why is it salty compared to the fresh water from rivers, for example? That's because the seawater is full of minerals in solution inside it. In particular, the most common mineral in solution in it is exactly NaCl, sodium, chloro, and chlorine. So common kitchen salt. So essentially that's how gypsum, but most importantly kitchen salt, are precipitated after a basin is lost. It's lost, it dries out due to excessive evaporation. We can see this in small in the Larnaca Lake, but you can think that essentially 5.5 million years ago, in the Messinian time, the whole of the Mediterranean was like a giant Larnaca Lake everywhere. And in fact, you can find salt that are also called evaporite sediments. They're called evaporite sediments because they were created by evaporation at the bottom of the entire Mediterranean. So it's not only present in Cyprus, it's not only present in Egypt, it's present throughout the Mediterranean, present-day Mediterranean, and also around the present-day countries, that are above sea level surrounding the Mediterranean: Italy, Greece, Cyprus, Libya, everywhere you can think of. There are present these Messinian evaporites that were all formed at the same time due to this huge event that happened 5.5 million years ago, where the whole Mediterranean dried out. Okay. And you can see this seismic section showing the geology, the subsurface geology. This goes from 200 to about 9,000 milliseconds, almost like meters, not exactly meters. From the Cyprus economic zone to the Lebanese economic zone, so a very, very long area, very, very large area. You can see it in this map, the location. This is the Lebanese coast, and this is essentially just to the south of Limassol, we can say. So a very large area. That's the boundary between Cyprus and Lebanon economic zone. That's all sea. And then essentially in this section, you have these pink layers, which is present everywhere throughout all this long area, which is being colored in pink, as I said, which is exactly this Messinian salt. So this Messinian salt is widespread. It's present everywhere, as I said before, under the present-day Mediterranean and in all the countries that are around the Mediterranean. It represents the ultimate seal rock for most Mediterranean petroleum systems. So not only Zoars, but lots of other Mediterranean geological systems that produce oil and gas, and they hold it in place. They rely on the Messinian salt as the ultimate seal that stops the oil and gas from flowing to the surface and being lost forever. Okay, so this is getting close to my conclusions, and that's an interesting question. Are there other Zoars waiting to be found in Cyprus, for example? That's a nice section, nice geological section, sketch, essentially a sketch. Each different color represents a different rock layer. Okay, obviously the older ones are the ones that are deepest, and the youngest ones are the ones that are more superficial. This is Egypt areas, so Egypt economic zone. This is Cyprus economic zone, so it's a section that goes from the south towards the left to the north towards the right, all in the offshore. This is all offshore. Okay, this in blue here is the sea, is present day sea. Here there is the symbol of a well, which is exactly Zoar, and this is exactly the upside down bucket shape of the Zoar trap. Okay. Do you recognize any other similar shape involving similar colors and similar patterns signifying same rocks towards Cyprus? Yes, there seems like there is a lot, according to this interpretation, according to the sketch, which has been drawn by Dr. Nicolaou. So indeed, there is a lot of hope that the Eastern Mediterranean as a whole, and particularly offshore Cyprus, can give us a lot more happy surprises following essentially the Zoar petroleum petroleum concept, with the same meaning, the same type of source, the same type of reservoirs, same type of seals, and the same type of structures. Very good. So, to finish off, if you want to know more about this topic of petroleum exploration in Cyprus, geology, petroleum geology, but also anything else that happens after discovery, a gas and oil discovery is made, what happens? Well, first of all, how to drill a well, then how to develop your discovery, how to produce gas and how to and oil, and how to bring it to your eventual customers. You know, the whole cycle, the whole exploration, development, and production cycles. You should consider joining some of our courses at the University of Nicosia in Cyprus. We have a very well-rounded programs which talks about everything, really. It gives you a lot of knowledge in all of the fields, with courses that are run by experts of the sectors. I am running, for example, courses of petroleum geology, formation evaluation, and safety and reliability, for example. And also we have developing network of industry contacts and industry collaborations. Okay, so we can offer programs in BSc of 4 years in oil and gas engineering, MSc, 3-semester oil, gas and energy engineering, and also we can cater for PhD, oil, gas and energy engineering. Each of these programs can be part-time and full-time. Really, you should have a look if you're interested to the website. I will leave below here the relative address, web address you can go and visit. And if you like any further information, please do not hesitate contacting us. And I look forward to seeing you next academic year. Thank you very much for your attention.